Let us start with our session number 4 on passive strategies for reducing cooling demand with Marco Schmidt, Dr. Yosr Allouche, and Professor Mark Nieuwenhuijsen. And please welcome Marco Schmidt, who works for the Federal Institute for Research on Building, Urban Affairs, and Spatial Development, and at the Technical University in Berlin. And today we are going to learn about energy-efficient passive cooling and shading. Welcome, Marco.
Yeah, Julika, thank you very much, and Daniel as well for the invitation. Um, I'm working at this institute. We are part of the Ministry for Construction, and at the same time, I'm working at the Technical University. I have at this moment 11 projects on energy efficient cooling financed by the Ministry of Economics. And I have another project. Maybe you can show the first slide. It's already online. Yeah, that's me with my first slide. And on the left side, this is a project Bunker St. Pauli in Hamburg. This is financed by the Ministry of Environment for climate adaptation strategies. It's a Second World War bunker which has been redeveloped and greened. So my 11 projects I'm working on energy efficient cooling are based on evaporative cooling, on geothermal cooling, and on green strategies, so facade and green roofs. So the next slide, please. Yeah, I would like to, it's quite provocative if you compare that maybe to the sessions yesterday. I would like to announce never use electricity to cool a building. It's inefficient, unsustainable, and unhealthy, like you see on the small picture. Because if you're using electricity, you will always increase the urban heat island effect. Every kilowatt hour of electricity you use will be converted to exhaust heat outside of the building. We are getting more and more of these split aggregates worldwide. We have additionally this problem of the HFC phase down. But I would like to give you another insight what would be possible for buildings, because in my view, it does not make any sense to provide cold water inside to keep your building at 26 degrees. So the next slide, please. Instead of electricity, just evaporate water. And that's how our environment is cooled. Nearly half of the incoming radiation of the sun is converted into the evaporation of water worldwide. If you're now going to urban heat islands, you shift rainwater into sewer systems and they disappear and they don't have any chance to evaporate. This is currently the Institute of Physics in Berlin Adlershof. The next slide, please. And here we evaporate rainwater outside of this building in planter boxes. And they are planted with 450 climbing plants growing out of artificial substrate. We have a constant water layer inside of this boxes of about 5 centimeters, and the plants, they can get the rainwater just by growing inside of the area where the water is supplied. Here you can see that we provide an evaporative cooling of 280 kilowatt hours per facade per day. It's like a sinus curve. That's what I love as a scientist. These are real measurements, not simulations. Yeah, so the south facade, we can irrigate quite exactly the water layer inside of these planter boxes, and by just a small swimming sensor. And then we switch on a valve, and the valve will provide about 10 liters just in one event. And so during daytime, if the plants evaporate water, and during night, it's nearly zero. Next slide, please. And especially if you compare that to conventional blinds in front of your building, I would say the plants are better, yeah, because they evaporate water. And so the long wave emission inside of the building is reduced more than by 8 times. We have a goal temperature inside of our building of 26 degrees. And if you compare now the glass temperature, so the plants are growing in front of the windows. In the summer, they provide shadow and evaporative cooling, and in the winter, the plants, they lose their leaves, and the radiation will enter the windows. This is suitable for our situation here in Germany. In other countries, you might even provide during the whole of the year. It depends on the plants you're using. And you can see that if your conventional blinds will go down, you can reduce the surface temperature of the glass from 48 degree to about 32. Then suddenly, if you have a higher wind speed, the conventional blinds will open again, then they might close again. Just behind the plants, you have the leaves, and they provide evaporative cooling, and therefore the long emission inside of the building is reduced by more than 8 times. The next slide, please. Yeah, this is the next slide. And if you now calculate the demand for the energy consumption inside of the building, it's a primary energy demand for this building in Berlin, Adlershof from Humboldt University. You can start with a simulation for how much this building needs for heating and cooling. And because we have more than 70% of glass in front of the building for a south-orientated office, that would be the demand for heating and cooling. If you have no sun blinds at all, or if you have conventional sun blinds, or if you have automatic controlled sun blinds. And on the right side, these are the real measurements. So if you compare now the conventional sun blinds, this reflects the simulation before, but we don't have any simulation for green plants. And on the right side, you can see that you can reduce the demand for cooling nearly by 50%. And you increase a bit the demand for heating in winter time, and for lighting inside, because you cannot control it, but the plants are much better. The next slide, please. In this building, we are using rainwater as well for evaporative cooling in air conditioners. And you evaporate rainwater into the exhaust air, not to get an increase in humidity inside. And if you compare, because we have in this building 3 parts of cooling, we have absorption chillers of York, compression by train, and adiabatic cooling in air conditioners. Adiabatic cooling with rainwater costs 0.1 cent per kilowatt hour. If you would use tap water, it would be 0.7. Compression is 9 cents per kilowatt hours, and absorption 60.1 cent per kilowatt hours for German prices. For example, the compression system was promised that we have a coefficient of performance of 3.7, but we measured 2.05. And this is quite typical. So we are promised normally laboratory works, but if you compare that with the real performance during a year, it will drop until 2. So, yeah, and therefore, the next, I think you can, it's 160 times more expensive or 90 times more expensive if you compare this to evaporative cooling. The next slide, please. The next. Yeah, another option, no, before this one. Another option is you evaporate water directly on copper pipes. This is a concept coming from Switzerland, and I evaluate that currently in 2 buildings in Germany, in Taz Publisher and in the Böll Foundation. And here we have a measured coefficient of performance of 80. So 1 kilowatt hours produces 80 kilowatt hours of cold, and the cold water inside of the copper. So it's an open evaporation system where you evaporate water on top, and the cold water inside will cool our servers inside of this building. In the winter time, the exhaust heat from the servers are used to heat the building, and in the summertime, the cold produced by this system is distributed just by convectors you see on the lower left side. These are convectors which are using just a difference of 2 degrees. So with about 22 degrees, and you can cool a building and keep it on 26 degrees. And in winter time, you're using, for example, 25 degrees of heating, and then you can keep the building temperature on 21. So that's all for me. Last slide. There are some links, yeah, where you can download some publications from us. And yeah, I will be grateful in the upcoming discussion. Thank you very much.
Thank you very much for that interesting presentation. Well noted. You can cool down your room temperature and at the same time you heat up the planet. Okay, so show some reaction to Marco Schmidt, leave some applauding hands, share some hearts. Thank you so much, Marco Schmidt. And I see you participants using the chat already for questions. Thank you so much. For our live Q&A session, we have to wait until the end of the session. And queridos hispanohablantes, disculpen que no funcione la traducción, estamos trabajando en ello, ¿ok? Bueno, let's say goodbye to Marco. Thank you so much, Marco. And with this, I would like to invite Dr. Yosr Allouche. She is the Director General of the International Institute of Refrigerants, and she will talk about extreme heat and how emerging technologies can provide a response to it. Hello, Yosr.
Good morning, everyone. Thank you so much, Yolika, for the introduction. Just a small rectification. It's the International Institute of Refrigeration. So we are not only dealing with refrigerants, but with the refrigeration systems. Yeah.
Thank you for that clarification.
Yeah.
The stage is yours. Please make sure to always say next slide.
Okay.
All right.
So if I well understood, I'm not able to take the control, right? Because there are some graphs I would like to point, but okay. I will do my best to make it clear. Okay, so good morning, everyone. I'm very glad to take part of this session speaking about some emerging technologies in response to extreme heats, and I will show several accessible approaches to sustainable space cooling. Next, please. Okay, so a holistic approach which uses conventional technology but in an optimized way. Speaking here about district cooling, a technology which is or which provides cooling needs for a whole city. It has multiple benefits in terms of energy efficiency as centralized cooling systems with higher efficiency compared to individual units. It is leading to significant energy saving. And also a lower environmental impact in terms of operational reliability as the centralized plants, they offer an ease of maintenance and consistent cooling services. So this is a technology which is becoming widely applied. I'm here presenting the case for Egypt, for example, as the country hosts the largest district cooling plant in Africa. It is located in the new administrative capital. Now, I mean, this is a new capital emerging in Egypt with a capacity of 50,000 refrigeration tons able to be extended to 64,000 refrigeration tons using cascades of 11 centrifugal chillers and 10 absorption chillers, which offers the possibility also to make use of the solar energy or the waste heat for the thermal compression. I will speak about the thermal compression in a minute. Next, yes, thank you. So still in terms of approach, reducing the need for active cooling by adopting a holistic approach here, navigating both the macro and micro solutions can also help a lot. This can be achieved through the reduction of cooling load. This means that less direct and indirect emissions, so direct from the refrigerant leakage and indirect from energy consumption, less stress on the grid, and also less cost for the consumer. So to reduce the load, this requires intervention at various levels to tackle the heat island effect, as Marco was pointing out earlier, because of the urbanization, also because of the limited vegetation. The building materials also contribute a lot to the heat island effect. The materials we are using as the asphalt, the concrete, and air pollution, which increase the surface temperature of the building up to 24 Celsius actually. So to reduce the cooling needs in the building, so this is the second step, which can be addressed through passive design, which favorize the best orientations, the shadings, the material selection, the natural ventilation, and new building practices. Actually, they are not new. You will see in the next slides, they come also from the history, which should be implemented through enhanced building codes as well, and new standards today. The third step, and then we cover the remaining cooling needs with energy efficient and innovative cooling technologies using environmentally friendly refrigerant. In here, natural refrigerants clearly play a key role. Next, please. Passive cooling, so it consists of innovative techniques and technologies aiming at treating heat at various phases. There is the heat prevention and the heat modulation, which require interventions at architecture level, and the heat dissipation, which involves engineering interventions. I'm showing here so some data from UNEP, where it is stated that passive cooling techniques can reduce up to 24% of the AC demand. So including these measures in the building energy codes and promoting and reinforcing the building energy codes as a regulatory instruments tool for national authorities is very beneficial in terms of economics and environment. Next, please. Some photos here I'm showing. So in terms of architecture, as I said, this is not something new. There are lessons to be learned from vernacular architecture and old buildings that should be the base of the architecture today. A nature-based approach to provide space cooling that can reduce or avoid the need for mechanical cooling while maintaining the thermal comfort. As said Daniel yesterday, it's about having the thermal comfort actually actually appropriate temperature for humans. So we can see here some wind catchers as an example where the outside, so if you look at the figure at the corner to the left, I will make it. So this is an example where the outside air is introduced to the building. It undergoes a process of evaporative cooling. So Marco has spoke about it. I will also say a few words about it in the next slide. Fresh air is then circulated and ventilated to the space, and hot air, due to the density difference, leaves through those catchers that you can see. Next, please. Now, in terms of engineering passive cooling, so it's about heat dissipation. It can be done in the ground, sorry, to the left, as you can see the left, the middle figure, in the water, or in the sky. So using the ground as a heat sink is possible in almost all the climates. So near the surface, the ground and air temperatures, they are almost the same. From a depth of 2 to 3 meters, I'm not sure if you are seeing the figure I'm speaking about, is the one to the corner in the left. The temperature approaches the annual average ambient temperature, actually, which is below the room comfort temperature in almost all the climates. For this approach, it is important to state that an adequate system design in terms of depth, diameters, length of pipes, and air velocities are required. The middle figure I'm speaking about here, water, can be also used as a heat sink, in particular in the areas where aquifers are available, which temperature is often in the range of 10 to 15 degrees Celsius, which is also useful for cooling during summertime and preheating during winter time. So I'm showing here the summer and winter figure. So this consists in drilling 2 wells, one on the warm for the warm water withdrawal, and the other one for the fresh water rejection to the underground heat exchanger. Also, surface of the lakes and seawater can be also used, but here there is some problems related to the corrosion, and then suitable materials for heat exchangers need to be considered. I would like also to point out that despite the performance of the solution, the major limitation is related to the high capacity, is the high capital cost of these technologies. Night ventilation to the right now through natural cooling. Forces involving wind pressure difference are also often used for office buildings. An HVAC utility which is preferred in climates where there is a large difference between the minimum and the maximum temperatures over the day, as for example in Central Northern Europe or in arid climates. Next, please. Still in heat dissipation, radiative cooling is a process where the surface cools down by heat radiation in form of infrared energy to the colder atmosphere. It's a phenomenon where which is effective under clear skies in dry conditions, as clouds and humidity they tend to trap the infrared radiation. Here I'm showing a nocturnal radiator, which is used and which consists actually of surface with specific material engineering, which are designed to maximize this cooling effect during the night. You can see here a comparison in the figure to the left. So a comparison with a regular roof. So these are surfaces which absorb the minimum heat from their surroundings, higher reflectivity and higher emissivity in the infrared spectrum, which allows them to be effectively radiate the heat to the atmosphere. They can be integrated in the building under different configurations. You can see to the right hand side, and they offer the possibility to apply cold storage for AC application. A wide range of also phase change materials are available for this. Next, please. Evaporative cooling, Marco was speaking about this. I believe I cannot introduce it better than he did. It's another passive cooling technology, historical techniques also, which provides comfort cooling. It's called adiabatic cooling, as only heat exchange happens between the air and the water. So in a very simple words, the process is about introducing the water directly into the outdoor filtered air stream, this middle figure I'm showing here, through spray system or a saturated wetted pad, so that figure to the corner and the right. The hot and dry air streams provide the heat for water. Heat is absorbed as water, it evaporates. The dry or the air dry bulb temperature is lowered and the air humidity relatively increases, but it never reaches 100%, and the wet bulb temperature also remain the same. The cold and fresh air is then supplied to the area through the supply fan that you can see here, and the excess spray water is collected and repumped. Again, you can see the middle figure here. So evaporative cooling, as Marco said, is a technology which is very promising and should be widely applied as well. Next, please. Absorption systems or thermal compression system, they use water lithium bromide or water ammonia as refrigerant absorbent couple. So basically the refrigerant here absorb the heat. So I'm here trying to explain this figure, but I'm sorry, I'm not able to use the pointer. I will try to explain it to my best. So basically the refrigerant absorbs the heat from the water loop in the chiller, and then it gets absorbed by the absorbent. So the mixture is then driven to the generator, so that at the top, where both refrigerants and absorber, they get separated by increasing their pressure through applying this external heat source. Once separated, the refrigerant releases heat into the environment through the condenser that you can see at the top of the generator. So this is to say that the mechanical compression is replaced by a chemical absorption process that uses both the heat and the chemical, how should I say, affinity to achieve the same pressure range achieved in a conventional chiller. So absorption chiller represent multiple benefits related to the energy efficiency when using specifically the waste heat or solar energy, and then reduce the environmental impact. They do also use natural refrigerants, which have no impact on the ozone layer, on the climate. We have no issues with TFA, PFAS, and all these things, but also have some limitation compared to a conventional vapor compression system in terms of high capital costs. But then we need to consider that the operational costs are also reduced, which is related mainly to reduced energy consumption when using the waste heat. They have also lower capacity range compared to mechanical and complex design when which requires actually some skilled technicians. And here I would like to attract attention again about the appropriate trainings that we need to deliver to technicians, specifically when it comes to the use of natural refrigerants. Next, please. I think this is my last slide, actually. Thank you so much. I hope I was not too long. I'm very happy to answer your question. Thank you.
Thank you so much, Yosr. Yes,
thank you.
People applauding. Thank you
Thanks.
very much. And thank you, all of you in this session, for using so many pictures and making it so visible. It's nice. Thank you. I see the discussion in the chat is already going on and taking up heat. It's nice. Go on like this. Thank you, Yosr, and we will come back and see you in our Q&A session. Let's move on to our next guest, who is Professor Mark Nieuwenhuijsen. He is a world-leading expert in environmental exposure assessment, epidemiology, and health risk impact assessment. And he's a researcher, he's the researcher, but he is also a professor and scientific director of the Severo Ochoa program and director of the Urban Planning, Environment and Health Initiative. Last but not least, he's head of Climate, Air Pollution, Nature and Urban Health Program at the Institute for Global Health. And during preparation, Mark told me that he doesn't care too much about the buildings. He cares about the humans and their health. So welcome, Mark. It's a pleasure to having you here with us today.
Thank you so much, Julika. I mean, you shouldn't have told them that. I mean, of course I care about buildings as well. I feel bad now that, no, but my kind of angle is from a public health, from a global health angle. So, I mean, I'm a public health professional. I study how our environment influences health. And in particular, I'm interested in the impact of urban and transport planning on people's health. And so that's why I want to give a few little examples. If you can put up my slide, please. I'm based in Barcelona. It's one of the fastest warming areas in the world, I think. Unfortunately, at the moment also we're dealing with the climate crisis. Next slide, please. And we know the impacts of what we see for the climate crisis. I mean, where we see, you know, to a large extent, warming up, extreme temperatures, what are occurring, but at the same time, you know, also flooding, wildfires, and also droughts. I mean, that we just got out of a drought here. Fortunately, we've had some rain as well. So my interest is in, you know, urban and transport planning and the impacts on health under the climate crisis that we have at the moment. Next one, please. So we know that the current rising temperatures, in particular the extreme temperatures, heat events, heat waves, can cause death and disease. An estimate, for example, in 2022 is that there were 60,000 premature deaths as a result of the extreme heat. I mean, the heat waves that we actually occurred. I mean, that would just happened often, you know, for a few weeks, 3 months, but short period. But at the same time, we've got these rising temperatures on average as well. That, and in particular, also cities are affected by this. For myself, we're working at the moment with a database of around 1,000 cities in Europe. Where we have some information on the health of people, in particular mortality rates, and also information on environmental exposures, including temperature. And that's kind of the context of my talk here. Next one, please. What we see is that in particular in cities and regions around cities that there is this increasing heat. At the same time, what we see is also decreasing green space. And we've heard already before from Marco in the first talk that, you know, green space actually is good for cooling, is quite important. So this is a bit of a concern that the green space, in particular in city areas, is going down, and that fewer people have exposure on green, and the green could help with cooling effects, but as I will tell you in a minute, also has other benefits. Next one, please. As what I said, we have this data set of 1,000 cities. We don't only look at temperature, heat island effects, rising temperatures, what we see, but also other things that go together, what are not good for health either. I mean, cities are a complex system, everything is related. So what we see, for example, is also that still these cities in Europe have the air pollution levels are too high, causing around 200,000 deaths each year. Also, what we see already that there is a lack of green space, which leads up to 43,000 deaths per year in the cities. Also, there is too much noise. 60 million people suffer of noise levels that are harmful to health. And then, you know, as what I said, you have the extreme heat. So there are a number of different things that actually come together. And for example, if you increase green, you can also reduce air pollution levels. I mean, these things are related besides the temperatures, what we heard. These things are kind of related, and that's what we actually study. If you're interested, if you're in Europe and you're interested, you know, how this pans out in your city in Europe, We have a website, isglobalranking.org, where you can see the current environmental quality in the cities and the impact on health, to give you some idea. Next one, please. So we've already heard from greening that it reduces temperatures. I mean, it's very beneficial in this way. But we know that in general, green infrastructure is also important because it reduces the risk of cardiovascular disease and cancer. Also, as I mentioned before, reduces air pollution levels and also noise levels. It often promotes people to do physical activity. Think about a park or a green street where people go walk around. It improves mental health. We have many people that have mental health problems. More green space, just looking at it, often increases your mental health. It also improves memory and attention. And as what we heard before, it decreases heat and heat island effects. I mean, overall, it also decreases premature mortality. So that's why it's very important to keep this in mind, that also when you think about greening for reducing temperatures for buildings, it also has additional benefits for people in many other ways. Next one, please. We've heard already before the heat island effect. Particularly what we see that the city centers are normally 4 or 5 degrees hotter than surrounding areas because of the asphalt, because of the concrete. You know, we have a lot of public space in our cities, like roads. Roads and streets are public space, but we choose to put a lot of asphalt there for the cars that we have. And that increases the urban heat island effects. Also, what you see at the same time, that cars are emitting heat. So having lots of cars around also makes the city already warmer, and therefore, you know, leads to a greater need to cool buildings and inside buildings. So these things are all going together. That's what I want to say. Next one, please. So in our 1,000 cities, we did an exercise to see how urban configuration affects things like urban heat island effects, air pollution, CO2 emissions. It's important for the climate crisis as well, and also mortality in our cities. And what we saw, that we could identify 4 types of cities based on the design, and what we call them, or we gave them the label. They're not exactly, but you know, we have on the left side what we call Model A is the compact high density city, and on the right side we see the green low density city, and in between there were 2 other types of cities. What we saw particularly for the compact high density city was that the traffic density per square kilometer was much higher than in the other types of cities. We saw also higher air pollution levels as measured by NO2. We also saw higher urban heat island effects, the surface urban heat island effects, which you have here, and also higher mortality rates in those cities. On the good side for this kind of compact cities, we saw lower CO2 emissions. That's what we want to do. I mean, we want to prevent, we want to mitigate the climate crisis. So these are good. On the other side, if you look at the green low density city, we see that the traffic density is much lower. There's much more green space. The air pollution levels are lower. We have also lower urban heat island effects, but we have more CO2 emissions. So in that way, you know, these kind of things go together. And what the main message is here is how you design your city affects what kind of urban heat island effects you're going to get and other exposures, and what you need to do to remediate this and to address this. So city planning in this way is also very important from this perspective. Next one, please. Then last year we did a study in 100 of those cities where we did some modeling exercise where we first estimated how many people or how high is the summer mortality due to urban heat island effects in those cities. And we found that 4% of summer mortality is actually due to urban heat island effects, to this increased temperatures that we see in the cities. That's quite a large number. I mean, if you think about it, you know, we have many deaths. I mean, 4% of that is quite high. Then we did a modeling exercise where we said, if we would increase tree cover in those cities, how much would this reduce the temperature in the cities, the urban heat island effects, and how many deaths could that prevent? And what we found was that currently there, on average, there's 15% tree cover in the cities. If we increase this to 30%, we could reduce the overall temperatures by around 1.3 degrees. This is an average over the city. We see much more in the city center, normally where you have the effects more, but this is on average. And also on average, you could prevent 1/3 of the premature deaths that are attributable to the urban heat island effects during the summer. So you can see, you know, the numbers perhaps don't look so big. I mean, when you look from a temperature perspective, but when you go to see what you can reduce in terms of premature mortality is quite considerable. And then also, of course, you have to realize that premature mortality is at the top of the pyramid of health. Below that, you find many diseases or health effects. We know there's more mental health problems, more cardiovascular disease, etc., what you actually can get. Next one, please. So what we should be looking at is changing our city environment to actually keep it cooler and not having the need so much to cool our buildings as such because of the heat. And for example, one of the things is to replace the current asphalt, what we have, and the many cars that we often see in cities, this very car-dominated city planning, what is still kind of the main paradigm, to something more attractive for active and public transport, for active and public mobility, which you have, and also a different use of public space. And this is, for example, what we see here in Barcelona. This is an example of what we call the super blocks, where streets are being pedestrianized and put in much more green. So you take away the source of the CO2 emissions and the warming, and you provide cooling through green space, and also a much nicer environment, for example, for kids to play. I just saw recently that in Berlin you have something similar, the Kies blocks. There's some discussion around this. It's interesting. I think it's also based on this principle. It's not always easy to introduce this new designs, new urban models, what I call them, but I think they're extremely important to cool our city centers. Next one, please. If you want to know a little bit more, last year I wrote a paper around this, was published in The Lancet, and also there's a lecture to go with it on a video that you actually can see if you want to know, more about this particular topic. Of course, I've got only a few minutes to explain here, and there's much more to say about this. Next one, please. Thank you so much. And if you want more, you always can email me.
Thank you very, very much, Mark. Let's clap the virtual hands, give your comments in the chat. Thank you so much, Mark, for your insightful presentation. And with this, we are going to enter into our Q&A session. And for that, I would like to invite the speakers of this session to join me again. So please, Marco and Yosr, come back to our virtual stage. And then I think we have one direct question already, which comes from Augustine Atassi. We will now give you the permission to unmute yourself. You just need to wait 1 second. And then if you want to, you can unmute yourself and ask your question directly. It's not working at the moment, so let's start with the questions from the chat. Let's see, remember that you can highlight the questions. Yosr, you want to say something? Go ahead.
Yeah, yeah. I just wrote you in the chat, and as I indicated before, I have a meeting at 10. Actually, I'm already late, but I can stay still 1 minute if there is any question.
Okay,
or
okay.
I wrote my email address if anyone would like to connect or ask a question.
Thank you very much. That is really nice. So, dear team, if you see a question directed to Yosr, please highlight it, and we will take the last minute. Or thank you for leaving your contact details, and we say thank you again and goodbye, Yosr.
Thank you so much. Thank you. Appreciate it. Thank you. Thank you.
Perfect. Okay. So let's take a look at the chat. We have so many interesting questions coming up. I'm going to start by reading out loud the first, and I have to do it slowly because of the interpretation. With 24 to 30% space, is city being roof that is high exposed impervious infrastructure, adding to UHI and underutilized for adaptation solutions? Is there any policy or guidelines or research to being centralized greening for these roofs? Marco, you're leaning forward, so. Or Mark, who wants to get to this question?
I think Mark, yeah.
Yeah, I mean, I think there are many initiatives. That's why what I've known or what I know of green roofing, green roof infrastructures. I mean that where there are projects going on, even here in Barcelona, we've got a number of them. Of course, the problem is, or that there are many challenges. I mean, it's not so easy to make a green roof. Often the buildings are not really made for them. And then it's also to do, as in many other cities, I think you have apartment buildings and who's the owner of the roof, what can you put actually on the roof? It always frustrates me when I can see here, like in Barcelona, if you look at the roofs, there's so many roofs and you think, well, you can put so many, either green space or you can put solar panels on the roofs or whatever, but under the current law, it's actually not allowed. And that restricts actually the use of these roofs. And unfortunately, that leads also to urban heat talent effects. I mean, one of the easiest way actually to prevent it a little bit is to paint them all white, but even that's often not done because that would reflect a little bit also the heat, but that's not done. And often you see darker roofs, gray or whatever, that absorbed a bit more heat. Unfortunately, then we also have here in Barcelona that often the building quality is not great, what leads to quite a bit of high temperatures within the buildings as well. But Marco, probably you work also with green roofs. I see on the walls quite a lot of green walls, but also you have green roofs, I guess, as well. And probably
I wrote
some of the challenges what are there as well.
I wrote my master's concerning this topic 1992 on green roofs and the influence on the urban climate. And so a non-irrigated green roof with just 8 centimeters already evaporates 300 kilowatt hours per year. This is quite a lot. So you get lots of evaporation. And this has a benefit, a high benefit for the building as well. I'm not a fan of just painting everything white, because if you paint everything white, it's the same like if you have a facade which is white or which is black. The heat doesn't disappear if you're in front of it. Once the radiation will be converted into long wave emission if it's black, and if it's white, it's like a reflection, like a mirror. So the only option to get rid of the heat is evaporation of water. And it's nearly 50% on the globe that is converted into evaporation just in urban areas now. So green roofs and green facades are really a good option. And as we showed in Hamburg, in the Green Bunker, this was constructed in 1942. Now we implemented 5 more floors on top, and we planted more than 25,000 plants. So it's nearly 5,000 trees and shrubs. It's 5 times more than the Bosco Verticale in Milano. I would say this is really an interesting project. So just visit us if you're once in Hamburg. The people are really great. They love it. They go on top, it's a public park, yeah, on top of a bunker of lots of concrete. So we implemented more space, like a hotel and a bar, restaurant, and we improved the urban conditions just in evaporating rainwater. I think that's an important topic.
Okay, thank you so much. We have another question directed to you, Mark. As cities will need some time to change to more green cooling, what is currently the biggest barrier for residents to install AC units, especially the people that are at high risk for heat-related premature death, which could be avoided by ACs?
Yes, I mean, I think as Marco said, ACs are not great in a way that it's better to go for green. But yeah, I mean, I guess for many of those people, it's more cost what is related to as a barrier. I mean, that it's buying the air conditioning systems, but then also running them. I mean, and we know that, you know, they're quite energy intensive, I mean, and can be quite expensive. So, for me, it's not the solution. I think there are easier ways, what we know to cool. I mean, I'm not a great fan of air conditioning, but of course we're getting an aging population, particularly here in Europe. I mean, more susceptible, and you actually need to do something because temperatures are rising, more people are dying or suffering because of the increasing heat. But best of all, we need to prevent further heating. So particularly we need to get rid of fossil fuels. I mean, of course, this is long term. But also, what I said, think about urban planning. I mean, you know, particularly in cities, we have so many cars going around that produce heat by themselves. I mean, it creates a very, not a very nice environment. And we can use that public space that we have for cars, use in a better way. I mean, that, and I see it now also here happening in Barcelona, where they put these big pots with trees in there. I mean, probably it doesn't help so much, but it actually makes it a nicer environment that people can go outside as well. Because in the buildings it gets quite hot, but people can still sit under a tree and have a bit of, you know, a nicer environment to be in. Probably Marco has also some comments on this. That
we have another question in the chat, Marco. I would read out this question first, and maybe if you want to come back to this.
Yeah, sure.
Because this sheds light on another topic, water and mosquitoes. So do you have any experience with plants and plant boxes with water in subtropical and tropical areas in relation to mosquitoes? We are working on projects in Africa and Brazil.
Yeah, I read and I answered already in the chat. Yeah, so mosquitoes, don't be afraid of mosquitoes. If you do it right, like all technical infrastructure, then there's no problem at all. You need to plant vegetation in urban areas because that's what's missing. Don't be afraid of plants. Be afraid of technical infrastructure like split air conditioners which are not working. There you have to be afraid for. Don't be afraid from plants. Yeah, I measure quite often chillers which are not working, which have a much less performance than promised. If you just provide plants, then mosquitoes are not directly, they are normally in direct water, in open water, so you don't have an open water here in this case of planter boxes in front of the building. The best would be always, if you have climbing plants, to plant them into the natural ground and use plants in front of your windows which grow on ropes. Yeah, this makes sense because then you can define how much of shadow you want to produce, how much of window you need to look outside, and how much of evaporative cooling you have outside. And green roofs, they dry out normally in the summertime, but you are using plants which can survive under these conditions, which store water in their leaves or in the onions, like allium. And so there will be no mosquito in a green roof. And I love Barcelona. Maybe, Mark, I would like to visit you once. Especially I was amazed about Antonio Gaudí, yeah, who implemented Park Well. This is a really good example how you implement already vegetation, and people are going into the park in the summertime because it's much cooler if you compare it to the normal urban environment of concrete and asphalt.
You're always welcome, Marco. Unfortunately, Pacuel is nowadays very popular. I mean, it's very difficult to get in. Others have enjoy it as well. But yeah, you really notice within the city, if you go into more, with areas with more trees and plants or whatever, it's so much cooler. I mean, and you mentioned there the park, but for example, we have also Rambla de Poblenou here. What is a kind of pedestrian street with lots of trees, cycling lanes on the sides, and it's such a wonderful place to walk in the summer because the trees keep the area so cool compared to surrounding streets where there are not as many trees.
Yeah,
Yes.
so if you do it well, yeah, so you can implement measures of green, blue infrastructure, we call it currently, or climate adaptation. That means you need just to plant trees into the streets, and they're cool, yeah, if you compare it to just a sun protection system, yeah, which has to emit long wave radiation and as well convection. That means hot air. So the only way is really to evaporate water by a street tree. That would be the best option. And we have a huge problem worldwide because we're losing 150 square kilometers every day in urbanization. Yeah, so middle class city appears every day, so we need to compensate that. And in total, we lose the size of Hamburg or Berlin every day worldwide in vegetation. So it's desertification, so we get more and more heat worldwide and less evaporation of water, and then we wonder that it's getting hotter and that we dry out. That's of course a reason. It's an unsustainable land use, so we have to work against and not to implement air conditioners which are driven by electricity. Always use water. Evaporate water, then you get precipitation.
And with that, I would have to close this session.